So thank you so much for staying here on Friday to listen to my talk. And I'm an engineer. So what I'm going to talk today is application of all this great science that we heard for 2 days. And you'll see a couple of the same pictures that Luke just showed us, but in a very different perspective. So remote detection of fissile material using Cherenkov counters. Before I start my talk, I want to tell you a little bit about motivation, why we decided to look at this work. The issue of security is becoming more and more important, and there are multiple programs that started in the last few years regarding national security and non-proliferation. And one of the focuses of this program in particular is low energy physics and detection. So I fit into this category. How do we create detectors to detect things that will help us to monitor nuclear materials in various applications, transfer or storage? So passive means are not exactly adequate when it comes to seeing materials that are far away, that are being transferred from one location to another. And I'll give you a couple examples what I mean. So we have to go into active approaches. Active approach means you have to use a source of radiation that's away from the material that you're trying to detect, and you try to induce fission or photofission. Then you look at the signature, and you can usually say what comes out of it in terms of fissile or non-fissile material. So previous work was done on neutron and gamma interrogation, and this work indicated that resolution of such detection systems is not really important because the feedback from fission and photofission is rather continuous than discrete. So we decided to use Cherenkov detectors. What is Cherenkov? I'm sure most of you are familiar with this concept, but just to give you an example why it might be useful, this is an MITR core. It's actually much smaller than shown in the picture. The blue light that we see on the picture is Cherenkov light. And just by simply looking at the picture, we can recognize the assemblies that are brand new, fresh assemblies versus the burn-out assemblies. And these 5 assemblies were freshly loaded about the week before the picture was taken. So Cherenkov light can be a useful tool in national security and non-proliferation. The question is, how do we use it? So today I'll talk about the problem of nuclear security and why we went into active interrogations. This is the topic that I get the most questions about, and you'll see why. Cherenkov counters in long-range detection. Excuse me. And then I'll tell you a little story how we built this detector and why it was such an engineering project. Detector calibration and background suppression were the main focuses of investigating how this detector performs, and I'll conclude with future work. So the problem of national security, we don't talk much about it here, but I just came back from a conference last month on nuclear applications, and that was one of the main focuses. How do we deal with this trouble? How do we ensure that nuclear material stays out of wrong hands? And we don't mean just material being transferred through the border. Think of clandestine reactors, the reactors that we want to detect, and figure out what's really going on. And let me tell you that a lot of the countries that are trying to build up their nuclear arsenal, they will not let you inspect the reactors, and that's a big problem at IAEA. So what does the US do? Well, the first approach was to improve control regimes, which usually fails, as we know. Manipulate black market as another layer of defense, and quite brilliant ideas came out on this layer. About 20 years ago, there was a rumor about red mercury as an essential part of building a nuclear weapon. Quite a few arrests were made based on who's trying to buy red mercury. Well, people at Los Alamos and Livermore can tell you it's probably not true, but it was a useful thing. However, people, the spread of knowledge allowed us to, not us, but people that are trying to steal nuclear material penetrate this layer as well. So here we are, the scientists and engineers. We come in this layer. We try to figure out who is trying to get what. How do we do that? Well, first of all, what we don't want to happen is that material to end up here and then at the shore. That's been actually quite a trouble. 12 million TEU, 20-foot equivalent unit, arrives at the shores every year. And it takes about 12 minutes to unload one of these containers and just ship it off. So how do you figure out where and what is hidden inside of this massive amount of containers? Moreover, if this is San Francisco, the last thing you want is this container to arrive at the shore. So one of the objectives is to detect the material before it reaches the shores. So as I already mentioned, the passive detection is not really adequate when you're trying to detect material that's 100 meters away. So you have to go active. What is active interrogation? Well, you have to have at least two things. A source of radiation. Usually it's an accelerator that emits gammas or neutrons. And it doesn't really make much difference which one you use. And then you have a detector to detect if anything inside the container of interest is present. This is a little misleading because the detector is shown next to the object. Usually the detector sits next to accelerator. So you might ask, well, if you're using very high energy gamma or neutron beam, you'll produce neutrons in all surrounding materials. What do? Do you mistake that for nuclear material? Well, not really, because what we're looking for mostly is delayed radiation, which you know is characteristic of fissile material. So what kind of detector do we want for this problem? Well, we always want something with high efficiency and expensive and fast recovery time. However, for this particular application, we need a couple other things. Large area. Why do we want large area? When your object of interest is far away from your detector, the feedback, the radiation feedback that comes back, intensity decreases as 1/r squared. So the bigger your detector, the more of the stuff you can get. So the angle becomes essential. The second requirement is the detector must be able to operate near the linear accelerator. When that thing fires, there's a lot of backscatter radiation that will affect the detector performance. And then scintillators, usually they get blinded, and they stay blinded up to seconds, depending on scintillator. So if you are trying to look at the radiation at a certain time scale, what you don't want is your detector not being operational. So we start looking at Water Cherenkov detectors because of a few reasons. First of all, they're mechanically robust and transportable. So if you have a system that needs to be transported, I mean, this active interrogation system, usually the requirement is for the system to be transportable by helicopter, which puts other constraints on us. We can manufacture detectors out of steel or aluminum. Cherenkov detectors allow reduction in gamma background because of the inherent properties of Cherenkov, which I'll mention in a couple of slides. And most importantly, the water does not exhibit radiation damage, and there is no blinding of the detector during operation. Another thing that's being done with Cherenkov detectors, this is not the focus of this talk, but something I also worked at Lawrence Livermore Lab, is monitoring reactors using Cherenkov detectors. Why would we want to do that? Well, the physics community always gives you these great tools to work with. It's our job to make sure that these tools work on the scale that we want them to work on. And usually when we talk about antineutrino detection, we talk about giant detectors. In this case, we're talking about maybe a kiloton, 1-ton detector. So rather small detectors. So how do we know whether the detector will work or not? Well, we didn't until a few detectors were built, and we analyzed quite a few of them. So Cherenkov detectors are useful, and as I already mentioned, we have quite a bit of experience with them. But this is the scale of the experience that we have, kiloton. This is the Super K detector that we already seen today. These are people trying to do maintenance on photomultiplier tubes that are 50 centimeters in diameter. So take this scale and make it the size of this podium. What kind of information can we get out of it? The reason these detectors are so large because of the antineutrino cross-section. Well, turns out it's possible. However, the problem is completely different. So what is Cherenkov radiation and why we like it so much? Cherenkov is a light in the form of forward cone, which is also a response of the matter to a charged particle traveling through the matter faster than the speed of light in that matter. So immediately, two properties come out from this definition that we like in the detection. First of all, there's a kinetic energy threshold. What does it mean to us? Well, the particle must have a certain amount of energy before it will produce any kind of radiation. This is great because it cuts down on the feedback from the linear accelerator, and also cuts down on the low energy background. The second property is Cherenkov is emitted in the form of a cone, which means there is directionality. So if we need to cut down on the background even more, we can exploit this property, which has been done in multiple detectors of large size. And the light yield of Cherenkov is concentrated in UV and visible light, which makes it possible for us to use tools like photomultiplier tubes. So how do we detect Cherenkov light using, how do we detect gamma radiation using Cherenkov light? This is just an example of Cherenkov for low energy gamma. This is 1 MeV gamma, and this is a high energy gamma, 10 MeV. So what happens when the gamma enters the detector? See the Cherenkov light's produced. It's shown in yellow, but it should really be blue. And few photons scatter around. A lot of them get absorbed. In this case, nothing made it to the photomultiplier tubes that is shown in purple. If a high energy gamma enters the detector, the picture is quite different. See that a lot more light is produced. The cone angle is much wider. And you'll see that the photomultiplier tubes will light up when they get a response from Cherenkov photons. It takes a while because there's a lot of light here. You see the chicken pox here. This is the response to the Cherenkov photons. So in fact, we can use Cherenkov light to distinguish between gammas of various energies. It is difficult, but I'll show you that it is possible experimentally. How do we detect neutrons with these detector systems? Well, it's quite similar. The neutron enters the detection system, the tank of water in this case, and the tank can be loaded with gadolinium or cadmium or other compounds with high cross-section, capture cross-section. So the neutron scatters around until it's thermalized to the point where it's absorbed in gadolinium. And gadolinium will excite, you emit a few gamma rays. In this case, there are 5 of them. Green. One of the gammas underwent a Compton scatter with an electron and transferred enough energy to the electron to produce Cherenkov light, and that's shown in the blue cone here. The Cherenkov light scatters around, and again, we have at least one photon reaching photomultiplier tube producing light. So Cherenkov light is indirect response of the tank to radiation. And that's how it's done. Simple enough, right? Now what happens if we try to put this detector in the laboratory and see how it responds to various sources? Let me start with saying we didn't really know what's going to happen because there's not much data on small Cherenkov counters. There's a lot of data on large counters, but the purpose of them is very different from what we're trying to do here. So we went through a few iterations of detector design, and we've done quite a few design models in GN4, which we did optimization analysis, and put it in the engineering software, and then finally we built the tank. And this is just to show you the scale of the tank. So it's a little taller than me, 2 meters tall, and 75 centimeters wide. That's the face of the detector. We used GN4 code because it allowed us to do not only radiation interactions like nuclear capture and electromagnetic interactions, but it's also a very good tool for optical photons transport. And that was an essential part of this model because optical photons is all we care about. So knowing that the code can capture it accurately was a big part of it. The detector design was rather simple because that was one of the requirements. If it's a transportable system, you want to keep it simple. And this is the aluminum body tank, which is also light-proof. We don't want any other photons getting into the detector, polluting the signal. So the detector is composed of polypropylene insert, which supports highly reflective material, GOR. It's 98% reflective. Why do we want it to be so reflective? Well, because Cherenkov photons are scarce as they are. So we want to preserve them as much as possible. We have an LED on the bottom of the tank for detector calibration and monitoring the stability. Have 6 photomultiplier tubes that are facing down. And the water was purified using both filters and DI unit. It's the construction that I got my hands dirty, really dirty with this project, putting this together and doing a lot of plumbing and soldering, as Lara was saying. Some of us spend a lot of time in the lab doing this kind of stuff. So what happens? We put it together, and we had 4 sources to see how the detector performs using various sources. First of all, let me point out that we use cesium-137, which has energy of gamma 662 keV. It's a great source because it emits monoenergetic gamma, so it's really useful for calibration purposes. However, it is not very useful for Cherenkov because it's right next to the threshold. The threshold is about 420 keV. So we weren't expecting to even see this source because the number of gammas that would be produced, the number of Cherenkov photons that would be produced is so small that it's probably impossible to see it. But we used it anyway just to check. Cobalt-60 thorium is a 2.6 MeV gamma emitter, and of course AmBe with the high energy gamma are the other sources that we used. This is just an example of the electronic system, CANE data acquisition system that we built together. So before we did any data acquisition with the detector, we tried to predict what's going to happen, and this was done in a GANT4 model. And you see 4 sources here. This is cesium. It's barely visible. I don't have background in the model, so it was nice and clean. You have a cobalt-60 source, thorium-232, and this is the AmBe. One thing to point out that the model predicted that we can actually distinguish between various sources. That's a big deal because that tells me that we can actually do, if not energy calibration, at least energy cutoff. When does that come important? When we do active interrogation. I already mentioned that in active interrogation, the feedback from fission or photofission is rather continuous. But it has photofission and fission gammas have energies above 3 MeV, and not much of a background has energies above 3 MeV. The highest you'll get is about 2.6 from thorium chain. So it was essential for us to figure out how can we put a threshold, energy threshold, and ignore everything below 3 MeV, only look at the stuff above 3 MeV. So the simulation told us, well, if you calibrate it properly, it'll be possible. What does it look like when we do it experimentally? It looked quite similar, actually. It's a little more smeared because there's presence of background, which smears things. And we were even able to capture cesium-137. Statistically, we didn't use it in the calibration, but physically it was there. One interesting thing to point out about AmBe that took us quite a while to figure out why there's a 2-peak feature, which is more visible in simulation, because, again, there's no background smearing in this case. AmBe emits 2 types of radiation, neutrons and gammas. And the gammas have 4.4 MeV energy, and most of this part of the spectrum is due to 4.4 gamma. However, this part is due to neutrons. What we didn't realize in the beginning, we had to simulate this, the neutrons will be captured on hydrogen in a tank of water. Hydrogen dioxides emitting 2.2 MeV gamma, which became its own peak here. And we picked that up on experimental results as well. We did quite a bit of verification to make sure that this was, in fact, a hydrogen peak. So we got all this data. How do we calibrate? When we calibrate in the lab using sodium iodides or germanium detectors, we usually have peaks to do that. We don't have peaks here. What do we take as a peak of the full energy gamma deposition? Well, it's Cherenkov detectors are not really calibrated to sources. They calibrated to photoelectrons. Keep in mind that this kind of calibrations are done for stationary detectors that are not refilled, that are not moved around. This is a different problem. We cannot rely on 1P calibration because of the electronics. So as soon as you change electronics or anything is changed, this 1P calibration does not hold anymore. So we have to do either LED or source calibration. Well, one idea that we came up with was to use the end of the spectrum for the calibration. Think of Cherenkov energy. When the gamma interacts with the detector, the most amount of energy it can deposit is through Compton scatter, which is head-on collision, forward scatter. This is the most amount of energy. But most likely, a lot of this energy will be lost from the detector. This is why we have this continuous spectrum instead of more or less a peak for 4.4 MeV. So if we use this end of the spectrum for energy calibration, and I keep saying calibration, but it really isn't calibration per se, and what we use word calibration in normal conditions. So if we use this end of the spectrum to assume this is the 4.4 MeV gamma or 2.6 MeV gamma, and plotted energy versus the experimental bin or the computational bin, we get pretty straight lines. And we can actually determine the slope of the line, which will tell us about what bin of interest we should place our cutoffs to. So that was an interesting task to do. The other task was to do background suppression. When you're in the field and you're trying to detect as much stuff as possible from far away, background is on your way. In fact, the count rate would probably be about the same as background, which is requires suppression as much as possible. So we've done a couple of things for the suppression. First of all, look at the majority of the PMT response. That's a similar thing that they do in Super K, but on a very different scale. We only have 6 PMTs. So we can look at the combinations of 1, 2, 3, or more. So this is an example of Spectra after we impose various conditions on the Spectra. Majority equals 1 means any PMT can trigger a signal in a detector. And you see there's a lot of low-level noise. When we start imposing majority equals 2 or more, the low-level noise is significantly suppressed. But why do we know that we're not losing anything from the spectrum? We monitor the spectrum by looking at the muon peak. Muons deposit so much energy in a detector, they light up all 6 tubes every time there's a muon passing through, especially in the vertical direction. So by looking at the muon peak, we know that it is really background suppression due to the low energy stuff. Another thing to look at is energy threshold, looking at the electronics. It's, as I already mentioned, not always the best idea. It's always best to calibrate it first and then determine based on your bin location, because things change. And using a combination of majority and electronic energy threshold, we can actually suppress background to the point where virtually non-existent in the low level. However, one thing to point out, along with the background, you suppress your signal. So black and red are the signal from AmBe, green and blue is the background. So if you take a look at this strict condition, majority equals 4 and a threshold of very high number, along with the background, we suppress the signal by almost 2 orders of magnitude, which is also undesirable. So in this case, it's all about the balance, and we're working on a model that will determine where the best balance is in terms of suppressing the background but not reducing your signal too much. So in summary, the small size Cherenkov detectors, and again I say small, but you can only call it small when you compare it to Super K or other detectors that we're used to. The small size Cherenkov detectors are not common. Think Super K. This is what we're used to. The objective was to construct a detector that is capable of detecting gamma rays of various energy, and not only detect them, but also discriminate between various sources, which we did successfully. We achieved significant background suppression by using various combinations of both electronic threshold and PMT majority. And we determined that one of the significant limitations of this detector was resolution, which is very poor. However, that was not a major contributor to the detector design. Look at the resolution. And such detectors actually becoming quite important tools in national security and non-proliferation. And this is 2 examples I gave today. The one, active interrogation, and the second example is reactor monitoring. And I can assure you that IAEA is very interested in small-scale Cherenkov detectors to determine what the reactors are doing. So just to conclude with the acknowledgements of my committee, Dick Lanza, who's here today. And of course, I'd like to thank Stewardship Science Graduate Fellowship for all the support that I received over years. And it was great being here every year. So thanks.